Hi, welcome everyone back to another Timber Design Society webinar. Today we'll be hearing about design specification durability of Glulam and Glulam-Steel composite structures. So we're doing a bit of a deep dive into a Glulam special here, presented by Woodman and Farhad Darani. First of all, thanks to all of our sponsors, Rotoblas, Mytech, Ibold, Xlim, Simpson Strong-Tie, Techlim, Eurotech, and Prolam for all the support over the last months and years. The next TDS webinar next month will be a specification special for mass timber. So we'll be hearing more about CLT, Glulam, and RVL specifications. Matt Davies will present that next month, so stay tuned for that. And there are a couple of upcoming TDS events that might be worthwhile for you to look out for. There's a Designing and Build Better with Timber seminar up in Auckland on the 27th of November. And there's a site visit in Wellington, which is quite exciting to look at the Parliament building. Both of these events are carried out together with Midrise, and unfortunately I say the site visit is fully booked, but I'm sure there will be a waiting list if you're still interested. We have upcoming TDS scholarships. This is professional development grant at the moment, which is open until November the 10th. So feel free to snap the QR code and follow the link. I just leave this up for a second just in case you have to grab your phones. And again, as usually, if you have any issues that you come across in one of your projects or want to know something more about timber design, follow this link and provide us with some feedback on some new topics for technical notes that you would like to hear about in the new journals that we issue. Let's come to today's webinar, however. We've got John Woodman and Dr. Farhad Darani presenting it to us today. John Woodman founded Prolam in 2002. He has now 103 staff, is one of New Zealand's leading engineer timber specialists, dedicated to strengthening the building industry through innovation and quality manufacturing. With a lifelong passion for timber, he combines deep material expertise with a commitment to customer service and sustainable design. Under his leadership, Prolam has pioneered industry-first products like the PLX 20 beam and the PLX bracing portal, helping architects and builders to build better together. And then in the second part of today, we'll have Dr. Farhad Darani, a sales engineer manager at Prolam. His role at Prolam includes engineering design and product and business development. He's a chartered professional engineer with a wide range of design and assessment experience in New Zealand and overseas. Farhad holds a PhD in structural engineering with a background in research in seismic assessment and low damage solution. So I would like to pass it on to John. Please feel free to kick off the seminar today. John, over to you.
Well, good. Thanks, Bjorn, and thanks, Wider Engineering Society. I'm really pleased to be able to present today and just go through a few slides on Glulam and what it can do for you. And hopefully it's insightful. Be keen on feedback. We live on feedback. So what we can do better is what we're all about. Next show. Just having a problem going to the next slide for some reason.
Minimize here. Can you see our screen now?
We can see your screen. You might just have to click the arrows in the bottom left.
Sorry,
There you go.
we're away. So what is Glulam? Glulam over timber is engineered timber wood made out of gluing layers of structurally graded timber together. So we've got a Glulam example here. We've got LVL and then just our solid standard timber. A bit about the manufacturing process. So this is just a quick overview. So we've got procurement of our logs, our log processing, kiln drying, optimisation of the sawn lumber, finger joining together, treatment. We then transport it to our lamination site. Then we've got planing and finishing and packing. So just a bit on log procurement. So logs are sonically tested to assure the best recovery in the structural lumber. This tool has been developed in New Zealand. So the speed of sound through wood provides a direct measure of stiffness. So we specify a log grade of 3.1 meters per second. So that's the speed of the sound going through the log. Similar to what LVL, they specify a high sonic log as well. And Nelson, top of the south, is a really good place to get highly sonic logs, as the same as the top of the North Island. So we do have a great resource on our doorstep. Here's just a little video of them testing logs. So they'll mark the logs with a different colour for the different grades. So it's just a hit on the log, and it just reads the sonics through the tool, and away you go. So they'll mostly mark the high structural logs, and they'll separate them out and send them to the mills that specifically require the high density logs. Log processing, so logs are then cut through a mill into the required sizes and then filleted ready for kiln drying. So this is our little head rig here. There's a chipper canter here which grinds off the side of the log, and then our bandsaws in behind. Kiln drying, so our timber is kiln dried to a moisture content of 12 to 16%, either in a batch kiln or in a continuous drying kiln. This is a continuous drying kiln in here. This is an in-feed, and it just has a hydraulic ram in the bottom that just pushes that loaded timber through every half an hour. It pushes it about another 300 millimeters. So it gives it a real nice gentle dry, because in the first section of the kiln, it's just it's got no heating coils. It's just got fans blowing air around. There is a bit of heater there that escapes back out of the actual kiln drying portion of the kiln. So it warms it up really nice and gently, and same on the outfeed on this picture. You can see the steam coming out here, so that's where it reconditions the timber as it's on the way out. Optimisation, so this is where we cut the lumber into specific structural and visual grades. So we have SG 12, 10, 8 and 6. So number one, we put a structural profile over the board. Then we put a moisture content profile over the board, and then a visual profile over the board. And it's not till that point there we decide how we cut this board up to optimise the timber out of it. So this is just a picture of the structural profile of a single length of timber. So there's 37 points that are graded here. And so every one of these bars is like 140 millimeters of that length of timber. So you can see the huge range we have in the structural portions of a single stick of timber. And that's because we're dealing with a living product as timber is. And so the highest grade here got up to an SG 17, and the lowest was a 8.9 here, but the average was a 13.35. So we cut out portions of that lumber, so everything above a 11.5 would go into SG 12, and then we'd pull some 10 out, and then there'd be some 8. And then this is, so over the average of a run, so on this one here, we're getting 52.9% PL12, 45% PL8, and 1.1% PL6, and a tiny wee bit of PL17. And then this is a visual grader. So this is all four sides of the board. So this is the face, this is edge 1, this is the bottom face, and then this is edge 2. So it's picking up the knots, and then it's telling us what we're grading at here. So we're getting some PL12 as a green, then we get some long waste, and then we've got some 8, which is the blue. And then this is our visual scanner. So this straight line LED here is picking up the visual grading of the board, whereas this dot grader here is picking up the grain deviation. So that's really important for our finger jointing, because we don't want the grain anymore on an angle no more than 12 degrees for finger jointing, to keep the structural strength of our finger joint where it needs to be. So then we come to finger jointing. So timber the same structural and visual grades are then finger jointed together to the correct length using glue for the correct service class. So we do some ongoing verification here. We're sampling 3 joints per shift, and be tested in each production line. So I've just got a little, this is a bit on our production record. So these are the records we keep every day for our quality control. So date, species, grade, moisture content, the resin type and hardener, the manufacturer of the glue, the batch number, expiry date, the service class type, clamping pressure on the finger joiner, adhesive spread, grams per square meter, service class, and then a gel check. So we use a 2-pot glue, so we do a gel check on the glue every day to make sure the batch is going off. And then this is just a little bit of so you can see has broken onto fingers, but there's a lot of wood fibre pull out. So that to me would be, I talked to our testing guy, he said that was 85% timber failure. So that's just showing you where it broke at. So it's 1500 PSI. And we have our chart up here. Sorry. So that size was 96 by 36. So the GL8 grading, we needed to break at 609 and we broke at 1500. So that just shows that we're above, quite a bit above where we need to be for our breakage. Yeah, coming to treatment. So treatment is timber is treated in a pressure vessel to the required hazard class. So we've got MCA or CCA, H3.2, H4, H5 or H6. And then we have the boron treatment for H1.2. So these are the pressure vessels here. These are the working solution tanks that get pumped into these vessels with the timber in it. And then that's our compliance report we get from IVS. For every 30 charges we put through, we have to do a sample test of 10 boards. So these all passed here, and the minimum we're allowed for chemical uptake is 0.75. So we we always aim a little bit above where we need to be there. So this is a treatment penetration test. So this is looking for penetration of the chemical into the blocks of timber. And then this is looking for heartwood and sapwood. So they've marked where the heartwood is here, or more like transition wood, really. And then we have to re-dry the timber after it's treated. So we're re-drying it back again to a moisture content of 12 to 16. And this is a little overview of our continuous drying kiln. So this is your preheat end coming through here. And this is the proper kiln section in the middle here, and then a conditioning section on the way out here. Coming to lamination, so finger jointed blanks are then machined, glued and clamped for the required length of time to cure the glue. So, and these are just a few examples of different ways we can laminate. And then, so our production records for the lamination process, so fairly similar to finger joining. We're taking thickness of the laminations, the moisture content again, resin, the start time of adhesive process, application process, and the start time of clamping. So that's quite critical for us because we're using a heat cured glue. So depending on the temperature of the day, we've got to get it into the clamps within a certain time period. So we're taking the temperature as well, clamping pressure, adhesive spread, surface class check, and a gel check again to make sure the glue is correct. Just a bit on standard. So this is the old standard that had the adhesives in there, and it showed the surface class 1, 2, and 3. So class 1 is for interior, class 2 is for exterior but protected, and class 3 is for exterior. And then it brings you moisture content and what have you there. So bond integrity test method. So this is for lamination. So we're using, most of our product is service class 3. So we're using the delamination test method B, pendants A. So this is the test cycle. I won't bore you with going right through that, but essentially we have a presser vessel where you fill it up with water. We put the timber in there, we pull a vacuum of 70 kPa to 85 for 30 minutes. And we release the vacuum and then pressurize it. And then we dry the pieces in an oven, and then we count the delamination from there. So these are a few bits that are in our oven. So you can see the stresses here that the actual timber is going through in the checking, and the deformation of the actual blocks of timber. So that's the stress we're putting it under before we actually do the delamination evaluation and testing. I've just got a few videos here of different laminating processes. So this is a radio frequency press, which is what we have here at Prolam. So it's laying up the timber on the infeed. So that's in the press here now. Then this is the RF energy, just shows you a bit of a side of the RF energy going into the press here to cure the glue. So it cures the glue by, it's a bit like just a big microwave. So it works on vibrating the water molecules into glue and curing the glue, so it's not actually heating up the timber. This is another one from Limnet. So this is a cold cure press, or it just cures the glue in the temperature of the room it's in. So feeding timber through a glue spreader. It's fairly fast, this, because these guys here were using PUR glue. So they had the PUR is very fast setting, but it also has a very short open cure time. So you've got to get into the press very fast, and so get into the press very fast and clamp it very fast. So this is unclamping now. Oh, sorry, no, that just finished clamping. So now it's turning this whole cylinder around, and the one that's on the fourth side, which will be coming onto the bottom, will have been fully cured. and then this is the finished beam, or finished beams coming out of the press and getting trimmed to length here, and then going down towards the finishing painter, like so. So this is a different press. So this is how they do curved beams. It's quite a long video. You better come back and look at this in your own time. But this is pushing the pillars into the right curve to make a curved beam. This is building up the lamillas. So bring them into the press, and then curving, pulling that round with hydraulic clamps. So quite labour intensive. There's no real easy way to make curved beams, but see here they are doing up the bolts or the clamps, flattening the beam out and pulling the pressure on the beams. Remachining, so after those processes, you got your final Glulam products machined to their final size. There's a few different machining finishes, so most of beams will be just machine finished. We can do a bandsawn finish on them, sanded and sealed, or pre-primed. Just a bit on durability, so Glulam timber is highly resistant to moisture, fungal decay, make it long-lasting and low-maintenance material, so we can treat it up to, again, from H1 to H6. So you got your H1 for interior protected, H3.2 for exterior unprotected, H4 for in-ground unprotected non-bracing, so for like fence posts and such, and then you got your H5 for in-ground unprotected bracing, so that's for your decks and pergolas, and your H6 for marine. So a few treatment options out there. So you got your MCA, micronized copper azole, so that's a bit more of a environmentally preferred product nowadays, using copper only, whereas what we're most used to in New Zealand is CCA, which is copper, chrome and arsenic. And then we have our Frame Pro, which is our boron treatment for H1.2. Just a few the standards we're operating to currently. So we've got AS NZS 1328 2025, and we've got a finger joint standard, and then our preservative treatment standard. Structural properties. So this comes out of the old standard as well. Now we don't actually have to make Glulam to any specific standard, and I mean in MOE, but this is what was in the 1328 1998 standard, which is what we're running to currently. So our GL8, GL10 and GL12. Set it so your visual grades and non-visual grades. So when stained, visual grade Glulam is a natural warmth, attractive appearance, can enhance the look of any building, can be left exposed, adding a unique touch to any space. When painted, visual graded Glulam can be made to blend in or stand out in any project. So this is for verandas and big project beams. You'd have a visual grade. Non-visual is where we use it for like deck bearers and deck joists, where it's not seen, or just standard house lintels. Coating requirements. So this is probably with talking more exterior product here. All exposed surface, cut ends, joints need to be sealed with a good quality stain or alkyd primer. By a single coat of alkyd primer coat plus 2 full top coats compatible with the primer, in accordance with the paint manufacturer's specifications. Dark colours aren't recommended, and this is because we have with the heat, with the dark colours heating up the glulam, it can cause checking, staining. So apply 3 coats of permanent oil-based stain on all exposed surfaces. Just a few shots of the glulam can be used, and that hands me over to Farhad for our timber steel composite solutions. Thanks, Farhad.
Yeah, thanks, John. So, hi everyone. So actually, John and myself, we were supposed to do this presentation separately from different cities, one from Nelson and the other one from Wellington, but because of the power outage in top of South Thailand this morning and then flight cancellation to Wellington, actually we ended up doing the presentation from the same room. And let's hope that everything with controlling the fire in Kaikoura goes well and not much people are affected with that situation. So I will be discussing a little bit about timber steel composite solutions. This is a product that we have developed and have been using, I think, since 2020, which actually includes laminating a steel bar on top of our Glulam beams. So I take you through the development process and different testing stages that we have done to develop this product. And then there are some side products actually using the PLX20 concept that actually we have been using and proposing to the market as well. So these are different configurations that we considered at the beginning for developing the system. And we were aiming to have something which actually offers suitable strength and as stiffness as well. So for example, here we can see that we have a bending stress of 40 MPa and 45 MPa for two different products, one being 240 by 90 and the other one is 290 by 90. And then we have also an increased modulus of elasticity as well, which is 20 and 21 MPa. So, and for the rest of the structural characteristics like tension and shear, we have used actually GL6 structural characteristics, which is the timber used in the PLX20 range. So different development stages that we went through. First was actually how we want to glue the steel to the timber. So we used a high-performing epoxy, and we did different development length testing and surface preparation testing to make sure that we get enough resistance out of the connection between the steel and the timber. For example, this is a development test that we did in Sion to come up with the best surface preparation and measure the shear strength that we get at the surface between the steel and the timber. So also 4-point bending tests based on NZS 4063. So just to measure the stiffness and the deflections. So you can see here we have tested two different variations. One is with 3 steel rods actually inserted and epoxy to the top of the beam, and then this is just a simple rectangular steel bar. So after these tests, actually we decided to go ahead with the rectangular section only, and then we did some strength tests as well. So what you can see here, there is a good consistency in the results for these different samples that we have tested, both in terms of the stiffness and strength. And you can see there is a little bit of a ductility as well, so you don't get a sudden brittle failure. So which is making a good point of difference between this composite beam compared to simple Glulam beams. So which is good, for example, for collapse prevention or life safety aspects in our design when we want to consider those in our design targets as well. So so currently we are actually using this beam in interior and dry conditions only, but we have been doing actually exposure tests for the beam. For example, this one here, there is a beam that we are testing exposed to different weather conditions, and we are measuring the long-term deflections and other aspects of changing I don't know, shape and stiffness of the beam as well. So this has been out there, I think, for almost a year now. And one of the main objective of this test has been measuring the creep deflection factor for the PLX20 beam. And the results has been very good. The composite section has been performing very well. And then we kind of backed up that experimental observation with these analytical procedures. We used a K2 long-term deflection factor of 2 actually in our assessments. And for the composite section, we came out to 1.26 and 1.23 for our 2 different PLX beams, which means that it performs better even when we look into it from the analytical perspective compared to 1.5, which is currently proposed in the standard. But actually, we have used K2 of 2 in our analytical procedure, so which gives also conservative results. But if your design is governed by long-term deflections, I think this solution actually kind of solves a problem very well. So then we have done some other development tests, specifically if, for example, for the services, we need to, so there are some standard small holes through the beams that during the construction they have to make, but we have had queries from architects and builders that are they able to make bigger holes into the PLX20 beam, and we have done different tests. Actually, we have done a test with a 150 millimeter hole at the middle of the beam. So for this test, the performance was very well. The stiffness and strength of the beam was not much affected as we expect, because the failure will be governed by Fletcher. And then we have done another test with holes very close to the support, to the end supports, and we did the testing. So the failure was governed by shear. So we have a very good understanding of the shear resistance of the beam. So, and we are at the moment we are working on a guideline onto which diameter and which location the holes could be actually relative to the end supports. And if we need to get too close to the supports, we can add some additional, steel plates for reinforcement. We have also developed a numerical model for capturing different failure aspects of our composite and Glulam beams, predicting the flexural and shear performance, that we can use that in our designs, either for our product development or if we have any specific design queries that we want to look into that a bit in more details. So out of plane performance of the beam. So this is actually the test that we have done, because the PLX20 beam sometimes it's used for beam as well. So we did a deflection and then a failure test for the out of plane performance of the beam. And so the timber is PL6, but the composite section actually performs better than a PL8 and somehow close to a PL12 beam. And because of the use of the steel bar, so we have a good deal of the strength in the beam as well, if the performance is going to be governed by the strength. So based on PLX20 beam, then we focused on some specific solutions based on the demand in the market and the requirements from the industry. So one of them is the PLX portal, racing portal, which is using the PLX20 beam as the beam or lintel, and then two PL12 portal legs at either end. So the objective for this development was to actually have a solution that is easy to manufacture, easy to install on site. So it's not too labor intensive. Builders, they don't have to involve fabricators and welders, which actually is the construction process very well. So this is the development process that we went through. So we aimed for two different variations. One was for the 3604 applications, and this is actually the test that the team they have been doing for our off-the-shelf solutions to come up with the lateral stiffness and lateral strength. We have also developed some SED variations as well. When, for example, there are some specific design target requirements such as SLS or ULS deflections or SLS and ULS capacities, so we can work with the engineering to their specific requirements and come up with a design that meets their specific requirements. So this one here, for example, we have combined a PLX20 beam with PLX20 with a steel bars as well for the portal legs as well. And so we have got a good performance in terms of the ductility achieved for this specific design. And so, as I said, so it's easy to install on site. You don't have too many people on site, maybe 2 or 3 people. They can install the portal frame within maybe 2 hours, 2 to 3 hours, which saves a lot of difficulty and time on site. And so the whole package is delivered to site, which is kind of in line with the concept of, you know, a prefabricated construction and modern methods of construction, specifically looking into the residential market, which actually involves sometimes not too efficient processes, but we have been trying to kind of make the process a bit more efficient and contractor friendly as well. So another product that has been developed based on the PLX composite concept is the PLX bracing column. So somehow similar to the portal, but the difference here is that the fixity is coming from the base connection. Again, the development tests and the performance tests that we did for developing this concept. Again, there are 2 different variations that we have been looking into using the bracing column. One is actually for 3604 applications, and the other one actually that we recently developed is developing a solution which can be designed based on different engineering needs in terms of deflection requirements and strength requirements. This one here is a concept that we recently developed and tested successfully, which involves a ductile link. What we have used here is we have the steel bar connected to the column, which gives enough bonding strength, and we kind of continued the bar into the fixing at the bottom with a neck portion at the bar, so, and directly connected that to the base. So the benefit of this concept is actually it deals with lots of other complications in terms of timber connection designs, such as, I don't know, cracks, crushing, and so we don't get that kind of degradation of stiffness and strength and pinching in the behavior of the column. So this one here shows the force displacement graph of this concept that we tested. So we can see that we have a very consistent and repeatable ductile performance, which is achieved for a timber structure, for a timber element, I think, which is kind of, as I mentioned, is covering those more complicated behavioral aspects of timber, specifically when it comes to ductility and considering resolving the ductility through timber connections. I think this concept has been working pretty well. So this is a short video mentioning the test that we have done for the concept. So the steel bar is actually being stretched here, the neck portion, and actually it provides the energy dissipation and ductility for the system. So, and as this system is developed for mostly for the PLX portal and PLX column, they are mostly developed for residential applications. Again, one of the queries that we usually get from the industry is challenges and difficulties for the achieving the required edge distance of the anchors. So we developed this anchorage system that goes with an angle into the foundation, kind of resolves the edge distance issue. And we have done some pull-out and shear testing to measure the resistance of the anchor. So one of the things that should be noted is that we have tested and developed this system for mostly 3604 applications based on the performance requirements for the residential buildings. But if you are, for example, doing a specific engineering design and you want to achieve higher performances such as C2 requirements for post-installed anchors or some more kind of a strict design objectives. So this system is not developed for those. So then you need to go through your specific engineering design. For example, you can use casting anchors and use chapter 17 of 3101 for designing the anchors. So I think that's kind of concludes my presentation. So just my last two slides show some of the other applications of the Glulam products, like bridge applications, which we are able to achieve the performance requirements for the resistance, for the loads, and also for the durability requirements as well. And some more kind of commercial applications. For example, this one here, we worked with the engineers and we kind of laminated LVL laminates on top and bottom of the Glulam beams, which kind of shows that the benefits of combining different engineered timber products to achieve the better performance is something that we can do, work with the industry in that regard as well. So that concludes our presentation, and we'll be more than happy to answer any question that you may have.
Yeah, thank you for this interesting presentation, the two of you, and for sharing details on your production process, but also the innovation of your hybrid portals. We're now moving over to the Q&A. So I've got some questions waiting for you. I will read them out by the interest of the industry. So they've been upvoted as you've been speaking. And then if you could respond to them, either of you, since you're in the same room, that would be great. So there's a few questions to go through, very interesting ones. Let's kick them off. The first one we've got here is probably a very, very common, very interesting question is, can galvanized fixings be used for MCA treated timber in a sheltered exterior environment? MCA is not explicitly mentioned in 3604. So is there any difference in which fixing can be used for MCA and copper treated timber? Just wondering if the smaller copper particles MCA have any effect on the durability of the fasteners itself. So what are your thoughts on that?
Yeah, our recommendation is anything that's exterior. You need to have stainless steel fixings. We've got that from our chemical supplier, Coppers. We do have some literature around that we could add to this presentation. And we've got a little bit from 3604 referencing for that as well. So while there hasn't been explicit testing done for the copper MCA, the micronized copper azole, whereas as there has been for the ACQ, so we're just going off the ACQ data at this stage until they've got consistent testing data for the MCA.
Right, okay. Thanks for that. Let's jump into the next one. Steve Bright is asking, and quite a few others have given it a thumbs up. For PLX portal frames, are these cut to sizes on site or ordered in as a kit? What ductility have you assumed? 3.5 is the question. Also, what causing the 200 BU limitation? Deflections or hold down connections? So it's a few questions in one.
Yeah. So yeah, good questions. So they are delivered to site as a kit set, but with flexibility on site to cut bits and pieces into size. For example, the lintel is delivered a little bit longer, so from the order, so they can cut at either end to make sure that it actually fits on site, and then they can use the fixings to connect the knee joints. Also the legs from the bottom, they can be cut as well. So just to adjust the height a little bit. And then they can just use our foot bracket with the installation instructions. For the column, PLX column, it is delivered a little bit higher, longer. So if they want to adjust the height a little bit, so they are able to cut from the top. In terms of the bracing units, so we have taken a procedure based on 3604 with some additional considerations as to how we can kind of adjust our bracing units because we are using, for example, a portal frame, and how we can kind of adjust the bracing units for a procedure which is developed for timber frame walls. So this is a combination of P21 testing plus some adjustment as to how we can calculate the bracing demand and ductility factor. The 200 BU's bracing unit limitation is a combination of I think 4 different things: wind bracing units and earthquake bracing units, and P21 testing procedure converts the SLS deflection requirements into kind of ULS bracing units based on the numbers that we read from the test graph. So it depends on actually what situation is governing that specific case. It could be a deflection requirement or a strength requirement based on P21 procedure.
So there's no one single factor, there's multiple factors that could govern it or are individual for each occasion?
The unit, yes. The bracing unit, yes, because it depends on how the graph is looking like. And there is a deflection range defined in the P21 testing procedure that we need to look into the graph, into that deflection range. But the overall failure and the overall performance of the system is something which can go beyond that deflection limit, which is defined in P21 testing. But where this bracing unit is coming from, it could be either SLS wind or earthquake requirements or strength requirements. It just depends on how the actually load deformation graph is into those equations.
Okay, thanks for that. I think if people would like to have a little bit more insight on this, they can contact you afterwards and find out the exact details. Let's move to the next question. Where's the best place to find the latest timber design properties for wet Glulam? So you mentioned service class 3 several times for the production, also shown that you are looking into exterior applications for the portal or the PLX beam. Where is the best location to find information on that?
We have it in our structural timber guide. So we have the structural timber products for dry and for wet use. So we've done our development testing on that ourselves, along with Dave King at Tasman Consultant Engineers, and have that in our structural timber guide. I could do a cut out of that and add it to this presentation if people wish.
Okay, no, thanks for that. I have not designed a curved Glulam beam before, but just out of curiosity, does the design property of curved beams change compared to a straight beam? And does it increase or reduce or remain the same in most cases?
What I've seen is people just use the same structural properties, whether it's curved or flat. Our specifier takes into account that we pre-camber our beam, so it takes into account that pre-camber so we can show you that the overall deflection might be 9 mils, but the deflection from parallel or straight is only 2 mils. So we can calculate that out.
And if so, there are various guidelines that people could follow for stronger curved beams with smaller radius, because due to the internal stresses, there might be some reduction factors on individual properties that have to be applied. I think there's more in standards and current best practice guidance available. So I'm just going through here. For the PLX 20 penetration testing, are you considering screw strengthening either side of the penetrations or just unstiffen? So if you have a penetration in the beams, how do you strengthen that, and how do you test it, and how do you consider it?
Yeah. So first of all, we find a location where the shear resistance and bending resistance of the penetration is not affected by the location, so which is not too close to the end supports. If that gets too close to the end supports, so the way that we have been actually looking into that is to put 2 additional plates, steel plates, at either side of the beam and apply some screws through these plates, so we can get that additional shear resistance that we want to achieve.
So what you're suggesting is that you have to put something on the outside face, screwed or glued. Is that kind of what you're sort of?
Yeah.
But we could look at that, couldn't we? Screwing each side of the hull.
Yeah.
If it's on the end of the beam where the steel's not there, we could look at doing support screws either side of the penetration.
Yeah. We can do that as well.
Yeah.
So, but we just, we had a look at, the best practice in the industry and what actually is common practice, and we kind of thought about those steel plates. But the other solution could be just using those screws at either side to provide some shear resistance through the diagonal tension performance of the screws as well.
Okay, it looks like there's still some room for so I'm sure that you appreciate if people give you some ideas, and we'll find a solution for it to test in your lab.
Yeah.
Next question from Nick. For the PLX column, the holding down bolt etch distance looks very small. How have these been proven to have a sufficient capacity?
So as I mentioned in my slides, we have done pull-out testing. I think I kind of answered this question. We have done pull-out testing, but these are based on the demand that we expect through our 3604 application and P21 testing. So if you want to have specifically design anchors, which is following, for example, C2 requirements or 3101 seismic requirements, then you need to do SED designs, and the current situation may not satisfy those requirements. But the tests that we have done, it was based on the demand that we have in expecting for our 3604 applications.
Yeah, so when we tested the column, we had transducers on the anchors of the column, so we knew how many kilonewtons we were getting on the anchors in the ground.
Yeah.
And then
Right.
we
Okay.
pull out after that with our pull-out testing as well.
All right. Next question is, what is the cost comparison for Prolam portals versus the typical steel PFC portals carrying the same loads, also for the bracing columns?
On the portals, we've had your QS do a comparison for us, which is on our website. It does alter per area quite a bit, especially in the current market. We know we're very competitive in the South Island, but in the North Island around Auckland, the steel fabricators are obviously being very competitive at the moment because it's a very tight market. So we're not so competitive there at the moment. But with your QS's comparison, I think over 4 portals of similar size, Prolam over against the steel portal, 4 different beams, I think we're about four grand cheaper. So he goes into a lot of detail with all the, the extra labour with the steel and the bolting of timber to steel to get it back to timber again, and that's where the saving is in the extra time having to bolt timber to steel on site.
Right, I think we've got time for one more question. I'm just going through. Something interesting about the finger joints. Closely spaced finger joints can detract from the aesthetic appearance of exterior Glulam members. So have you got any ideas on how to improve this problem, or other means to get around finger joints?
Yeah. Good question. So, yeah, at the moment we're using Resourcenil because we had to use Resourcenil for our code marked H5 post for in-ground bracing. So one way is to get around that is to go to a clear glue, which we're in the we're just currently doing some in-house testing on a new glue for that for in-ground use. And then the next process on that is to get brands to do their test so we can include that new glue in our code mark. But at the moment they wouldn't code mark any glue except Resourcenil for in-ground use. And the other way around is to get longer shocks. But because less of our timber forests are now pruned, so you can't get nice clear timber as easily now. And especially with our posts, what we found earlier when we started doing this in 2004 is that with longer shocks, you couldn't hold your post straight, especially when you only got three laminars. So especially our 88 by 88 or 112 or 135, they only have 3 pieces of timber. And we first started making them out of just full length clears, but we struggled to hold them straight. And that's because you got so much different variances between those 3 pieces. One would soak up more moisture than the other and actually pull the others over. So having shorter shocks in a post especially is an advantage to keep the post straight, because it randomizes the timber a whole lot more.
Right. Oh, well, thanks for your presentation, 2 of you, and for answering many of those questions. We haven't answered all of them, so apologies to those that we didn't get to. Maybe you can look through these answers and potentially answer them offline or get back to these people. I think that concludes our webinar, and thanks everyone for attending. See you next time.
Thank you.
Thank you.